Uh, Hello, everyone. Uh, my name is Vitaly, and today with me I have Ani, who is also from Red Hat, and I have Alex, who is from AWS. And today we are going to talk about ingest firmware update mechanism. So we are mostly going to focus on the cloud use case, and by that I mean that the owner of this host and the guest tenant are two different actors, right? So the guest owner cannot change anything on the host owner cannot and doesn't want to change anything inside the guest. Mostly, we are looking at getting predictable, meaningful launch measurements for confidential VMs. But in theory, this mechanism can be applied to other situations and other use cases. So the question like, why would you want to give the ownership of the firmware, which was traditionally owned by the owner of the host, to the guest, right? And it's quite obvious for confidential VM use case, because for confidential VMs, you are getting launch measurements, which kind of describe the state when your VM was launched. And now you are getting some opaque blob there and some hashes of it, which is like a firmware coming from the host, right? And you don't really know what's inside. It could have been solved by, for example, cloud providers providing reproducible builds of the firmware, but it's not an easy doable thing either. And I will talk why it's not really the full solution a bit later. Also, you may want to do some weird things with your firmware. For example, you want to build SVSM, which is stateful and which does attestation to your own attestation server. You want to hardcode addresses, certificates, everything, that you get all these things in your launch measurements, right? And the cloud provider obviously won't give you an option to do that. And once you've done that, you may want to do something while your VM is alive, right? You may want to change this, you may want to fix bugs there, right? So you need an option to update it while your VM is alive. So the question is, why would a host owner be interested in their guest bringing their own firmware? Because it complicates things a bit, right? And again, for CVM use case, it allows the provider of the infrastructure to get rid of this piece of responsibility, which is this blob of firmware inside the guest, which doesn't allow it to say, I have nothing to do with your CVM. Currently, it does if it provides this firmware. Also, a big problem for infrastructure providers is that they cannot really update this blob unnoticed, because it will change guest measurements. Some guests may not launch with these new measurements. And for example, what do you do when you get an embargoed CVE in the firmware, right? And you're a cloud provider. You cannot update it. The guest is going to notice and most likely crash, right? But if you don't update it, then you're kind of responsible if things go sideways, right? And somebody exploits this vulnerability. Yes, the question comes is like, why not just supply, why do we need ingest mechanism to supply the firmware? Why can't we use something like give away JVM, give it separately through the cloud provider? And the thing is that we cannot have firmware as a part of like guest storage accessible by the host, because in many situations with like real cloud providers, their host cannot access guest storage at all, because the storage comes through like special device which gets it from network something, and it gets like a virtual function and VME function inside your guest, right? So yes, a cloud provider could have solved it by providing a completely separate set of like APIs to manage your firmware, put it somewhere on the side. But again, it's like storing firmware requires storage, managing this. So it's very, very inconvenient for large scale. So now I'm going to hand it to Ani, who is going to describe how are we going to do this.
Thank you, Vitaly. Yeah, so So let's see how we're going to actually solve this problem. So before I go into the details of the various steps that we're proposing, we'll just have a quick overview of all the different stack components that are involved in our solution. And I'll revisit this slide later when I've described the different steps. So obviously there will be changes in QEMU because QEMU needs to interface with the guest, and the guest needs to tell QEMU the blobs, the different blobs that are part of the measurements. And then there is systemd, which is the UKI, that needs to have the support for recognizing the blobs and then loading it in the memory. So we'll get to the details later. And of course, also we need to change the firmware, in which case it's EDK2 to actually load kernel and initrd. So let's look at the overall picture of how this mechanism works. So it basically works on a two-stage principle. So first of all, the guest boots with the cloud platform provided firmware. And then the firmware starts UKI. Now, UKI will detect that the measurements don't match because obviously the guest is booted up with a firmware that's provided by the cloud platform provider and is not necessarily something that the guest can trust. So the UKI has is a container format, and obviously it has various sections in it, and it contains the actual blob of the firmware that the end user trusts and is measured. And along with that, it also has the kernel, initrd, command line, etc., all the usual other components that needs to be basically needs to be trusted as a part of the boot process. So the UKI may or may not do signature verification. We'll get to why that is optional a little bit later. The next stage firmware, actually, which is embedded in the UKI, is trusts the kernel image, the initrd, and the command line because the next stage firmware has hashes of this component built into its secure table. So this is exactly the reason why we the signature verification for these components is optional, because when the UKI was built, it was built in such a way that the hashes are known to the next stage firmware for these components. So so that's one thing. And then what happens is that the UKI loads these launch measurements into memory, and it tells the hypervisor where it loaded these launch measurements into memory. So the addresses and the size. And there is also the launch measurements can be mapped privately in the guest memory, or it can be shared. And the UKI also tells the hypervisor whether the particular launch measurements is private to the guest, or it can remain shared. And part of the reason is that when the hypervisor will restart the guest with these launch measurements, it has to make that part of the memory private to the guest. So we need to, so the UKI needs to tell the hypervisor which one is privately mapped and which one is shared. And along with that, it can also tell the hypervisor the target address. So the hypervisor can copy, say, the private launch measurement to that target address in the guest. And along with that, it can also pass the target CPU state data. So when the VM is relaunched, it can launch with those target values for the CPU registers. And so then what the hypervisor does is that it restarts the virtual machine, but it throws away these existing contexts, and it restarts the virtual machine with a new Ceph context. And along the way, it also makes the private memory private. And this time, it is actually running the VM with the firmware that the guest trusts. So since this firmware is trusted by the guest, it also has the hashes for the other boot components, kernel, initrd, etc. So then, after the guest starts booting, when it calculates the measurements this time will be sent over to the external attestation server, and this time it will pass the measurements check because it is running firmware which is trusted by the guest, and that firmware trusts these other next stage boot components like kernel, initrd, etc. So then when the attestation server sees that the measurements are good, it will respond back with keys that will unlock all kinds of secrets within the guest. So then at that point, we are all running in a secured state. And so all is good at this point. So some of this stuff Vitaly has already covered. And so I'm not going to repeat that. And so already I have described some of these steps in details. Yeah, so the other mechanism that we were, one thing is that we're learning as we are implementing this. So we are obviously making some small adjustments and changes. So nothing is written in stone at this point, but one of the proposals is to build a kill switch. So once you relaunch into secured state, then we have a kill switch mechanism where the guest says that this interface can be used only once. So you use it once, you relaunch into a secure state, and then you are locked in. You cannot use the same mechanism to again relaunch into a different secure state. So this is just kind of an additional protection in case there are rogue components within the guest itself that tries to relaunch again with something that's not very trustworthy. So, and let's see what else we have here. Right, so again, so revisiting this, so you can see that we need changes in the QEMU. Now, currently, right now, it is not possible to relaunch or kind of reset a QEMU-based virtual machine when it has already initialized its secure context. So what happens is that once the VM boots up, it's locked in, and the CPUs are not resettable, which means that if you try to reset the guest, it will just terminate. So that needs to be fixed, because now what we're proposing is that the VM, when it resets, it will reset and generate a new secure context, but it will not get killed. So that is something that needs to be implemented, and there's some refactoring work that I'm undertaking, which some of these refactoring is already posted in the mailing list. And then there are some machine changes that are necessary to make sure that the CPU states are, so the VM resets into the target CPU state correctly. So the systemd is mostly the systemd boot, and the UKI changes are necessary there also to be able to parse the firmware config and then provide these addresses and lengths of these blobs and mappings. And also there is EDK2 changes where there is a provision for EDK2 to figure out the platform and capability bits that are exposed by the hypervisor, because what we envision is that when the guest builds a firmware for the virtual machine, the firmware may not be compatible for the underlying hypervisor. And so what the EDK to do would be to check if this firmware is actually compatible. And then if it is not compatible, it will not undergo this process, right? And then, of course, then the loader will load the Linux and initRD into the right locations in memory and then initiate the Linux boot. So I will not go into the details of this hypervisor interface. You can look into the code yourself, which is in the resources section. But before we go there, I will let Alex talk about the demo. And we really are proud of what we can show here. So Alex.
Sure. I figured it's pretty boring to see all of these things without seeing them live. Small caveats on the demo. It does work. It does show you now that we're booting into a new BIOS and a new firmware and into a new kernel. This demo is not running on SeaBIOS-SMP, which is an implementation detail at the end of the day, really, because of the QEMU shortcomings, right? I don't know who actually thought it was a good idea to not implement reset logic in QEMU on SeaBIOS-SMP VMs, but this is the main reason why it's showing you this on non-confidential VMs. The rest of the code would look exactly the same. Second caveat before I go in is the actual ABI is in flux. So if you want to participate in designing that one and figuring out how exactly we simplify that hypervisor to guest interface, be my guest. We can talk after. So what we have is we first need to generate a firmware UKI image. We call that FUKI. It's basically UKI plus firmware that contains all of these components. Right? It contains an OVMF binary, kernel, and initRD. And then we need to go and invoke a normal QEMU that loads this particular binary. So if you look at the command line for my QEMU script here, you will see that we have a device firmware update, which is the one that allows us this magic, and that we really just, all we do is we just do an iPXE boot into into our FUKI image. That FUKI image now goes in and loads that new OVMF, and that new OVMF then goes and jumps, basically internally loads that new kernel. So you see this, it comes in. This is the UKI stub, the Linux loader stub, which loads a new debug EDK2. You saw that's scrolling by really fast. I can go back a bit. You saw that somewhere here. So the original EDK2 was a non-debug build. This is a debug build, so you can see it's a very different EDK2, very different firmware that we're running, and that one automatically loads a full Linux environment. A full Linux environment that now is our confidential VM. Interestingly, while I was getting this demo working 2 days ago at in between LPC and VM forum, just as a trivia, I was sitting in a park trying to get the demo working so it actually goes and we can show you something. And then this woman comes up and hands me a sheet of paper where she drew me in the park writing, like building the demo for you guys. So here we are. This is back to you.
All right, thanks, Alex. That was quite a sketch. Yeah, so if you want to look at some of the code here, so there is a changes. Again, like Alex said, all of this is a process of evolution. So things are changing and we're still kind of figuring things out as we go along. So it's all open for suggestions and other proposals of how we want to do this. So yeah, so all these people who are involved, thanks Vitaly for basically initiating this project within Red Hat. I got right away excited about this and jumped in. Alex, we had this conversation in FOSDEM earlier this year on this idea, and then so thanks to him for the idea, guidance, demo. Paulo is also excited about it, Yeah, I hope. Yeah. And yeah, so thanks to him for the guidance, and Herald, who did all the UKI stuff for the demo, and thanks to him as well. So thank you very much. If you have any questions, we're all here. Okay.
This may be a dumb question. I'm kind of still trying to get my head around this, but does this only boot Linux guests because you have to do this kind of fancy song and dance? And if it does only boot Linux guests, why don't we get rid of firmware completely, get the hypervisor to load the kernel, and init ramfs image, transition those to private, and then do the attestation on those?
I do not want to revive the Zen kernel init whatever path where you suddenly had to like think of this in a cloud scenario, right? One of the nice things we have with HVMs in cloud scenarios is you have a single reference image. You have one army that contains everything you care about. You don't have random floating around parts that you need to individually update and upload and then go and correlate in any shape and form. With this, you can continue with the current model that we have of booting. Whether this actually does the reboot underneath the hood is a complete implementation detail. Your OS image, the way it runs right now, would also boot into a kernel. And whether it's Linux or not, again, implementation detail. This is all up to you. This is just an EFI binary. You can basically, with this, keep your your current scheme of everything and just move your attestation boundary into your boot phase. Does it explain answer the?
Yeah, it does. I'm just trying to see if you can do that, but with a simpler mechanism of loading init ramfs.
Other vendors do it with other mechanisms. I prefer if we stick to a single boot scheme.
And the other issue is with confidential compute like TDX, you don't have the ability to load in anything except 32-bit unpage protected, so that if you want to jump straight into the kernel, you need some kind of shim to get you there. And obviously you can define ABI so that you can go straight to something, but that get back to then PV. And then you're working with hardware vendors to get them to define the TDX module spec so that it matches your PV spec, and it's just, ugh. So I get why you would do some of this.
So two things. First of all, I think you should build that on IGVM as a standard format to basically pass the state of your to pass your reboot state to the next VM or to the next boot state. I think that would be a perfect fit, because then you can benefit from other tooling around IGVM, like calculating the expected launch measurement and everything.
I can answer that one first. I looked at IGVM. It's a terrible format. Don't use it, especially for this use case, right? It's way too hardware specific. And this particular thing, like the whole interface we have, is like 3 firmware config files that contain a few bits of information. This interface is trivial. You can use IGVM on the other end. Like inside of the guest, if you want to use IGVM to then populate that data to the hypervisor, be my guest. But the actual interface to the hypervisor is way smaller than what IGVM gives you, because we're already assuming that most of the data is in memory. It's already well laid out, and you just jump in. Plus, actually the new design, this is as of last week, doesn't transmit any CPU state anymore. We just basically say we allow you to basically override the existingly limited sized BIOS region. Like just basically we give you the right access to the flash ROM for a reset. And then we just use the standard reset vectors. Everything is the same as everything everywhere else. And that simplifies it tremendously everywhere, because you can also reuse EDK2 code, which otherwise explodes.
Yeah, but as you are proposing that this is going to be used at multiple CSPs, you probably want some flexibility and make less assumptions about what is going to be booted. And with IGVM, you actually get that flexibility. You can put in a firmware in the Linux kernel. You can put in a firmware that just boots up. You can put in an SVSM in the firmware. You just get the flexibility with IGVM, right?
I don't believe it's going to be any different with that scheme, but we probably want to look at the actual layout and how this works to conclude.
So just one comment, which actually originates from you, that if you pass an IGVM, right, you will need to receive it on the host side and unpack it, for example, right? You will need memory for that. You may not have it on the host, right? And if the guest puts everything at once in its memory, right, then it just, and now please reboot me, right? You don't need a storage, even memory storage on the host itself, right?
so
it may be a problem for some cloud infrastructure.
I may not be up to date with the last developments, but I think it's just a way to do a fancy reboot. Like if you want to support AGVM or even if you want to support Windows, it doesn't really change because if Windows ultimately is an UEFI application just like the Linux kernel, right? Okay, then I remembered well then.
Correct, yes.
Okay, just to respond to James, me as a regular user of a confidential compute facility that a cloud service provider provides, I would never want to hand over my kernel and init.rd to the cloud provider. So I would never want to do that. No, which is where this is going, but don't give the kernel and the init.rd to anyone else, for sure.
Are we at time?
Are we out of time?
Are we or are we not? When is the next one? Oh, 4 minutes. Awesome.
Oh,
Next question then.
Reset. You can't really have the host do the reset for you once you're encrypted and all that jazz.
You
so
remove, you destroy all encrypted state, you recreate all encrypted state, and everything that transfers, it has to be shared state. So the old VM, the first VM that boots, the untrusted VM, puts all of its payloads into shared memory because they will be visible to the host anyways, right? They have to be because you're putting them in, including the firmware region. Then you destroy the VM context, you destroy KVM, you create new KVM context, you create a new vCPU, and then you convert the BIOS region, at least in the newest proposal, into private memory, boot in, shared states, shared memory stays exactly where it is. So early boot firmware goes in, reserves these shared regions where it knows that this memory actually resides because it can read them through a firmware config opaque blob that we preserve across that reset, and then it can bootstrap itself.
how do you attest to the firmware that you're loading then? If I understand correctly, you're hoisting it into the VMM through shared memory, and the VMM reflects that back into the new world. How do you attest to that? Because you can't put it into the initial measurement.
You do. Ceph-SMP contains everything there is into the in the measurement. Okay.
So
is
you'd
your
have to
question
have
is your question around the BIOS blob or about the kernel?
the BIOS blob.
Okay, the BIOS blob is part of your launch digest. You create a new launch digest because you're creating a new VM.
So are you not attesting until the second boot then? You're not.
Correct.
You're never attesting the
Correct.
first boot.
The first boot is
Got it.
untrusted.
Okay.
Plus, I think one piece that we didn't mention, this allows you KExec of confidential VMs.
When you're talking about BIOS blob here, does that include your ACPI tables?
That is up to the guest.
Yeah.
The
Sorry, I guess
guest
what I'm
may
really
or may not want to consult us for their ACPI tables.
What I'm really asking, I think, is does this actually help with the problem of ACPI tables that was raised earlier? How do you attest that in a way that you can reason about?
If you want to build a piece of firmware that embeds the ACPI tables, be my guest.
Yeah.
Like, not you.
It's like for ACPI tables, usually they come from firmware config, but if you, there's two ways. Either you trust that the cloud provider doesn't change them too often and have a contingency for when they change, or otherwise you embed them, cross your the ones that you know about, cross your fingers that they will keep on working even if the cloud provider changes them, but then at least it may fail to work in some cases, but it doesn't fail to test. You can get them from firmware config, compare. It's a matter of policy in the end.
Correct, and all of that is up to the guest. We are out of the picture, right? We don't mind as the hypervisor. It's guest policy. Cloud Hypervisor, for example, actually allows you to do exactly that. They have a way where you can just say, load this kernel, load this init.rd, and load these specific ACPI tables. So all of these are part of your launch measurement. Honestly, I don't think that eventually people will use EDK2 with this. It's going to be a tiny shim that only allows you to run this EFI binary, nothing else, no firmware config access anywhere, and everything you need inside this VM is self-contained. But I don't want to be the one building this. I don't want to have to be the one building it, and I don't want to basically provide this even, because that would put me into the confidentiality path again, right? And that's the whole point why we're doing this. If you don't want me in the confidentiality path, do everything on your own. If you want me, use my hypervisor and trust me when I say it's confidential too. we are out of time, is what the sheet says. So thanks a lot.